Hello, in this lesson, we like to go over how to find critical numbers and why critical numbers. Okay, let's recap what we have done in class. In class, we have defined what is the absolute maximum and what is absolute minimum, and absolute maximum. Okay, the definition of absolute maximum is that there's a function that is defined in its domain. And this function is every possible value is no bigger than the value at C for all of the x in the domain of the function. If this is true, that's f of C is the local maximum. And for local minimum, okay, the definition is similar, except we're going to change the directions of inequality sign, that every function value is no smaller than f of C. So we can say this is absolute max, absolute min. Okay. So we also say in the absolute maximum case, the language we use is we say f has absolute max at C. Okay, and the latter one, we can say f has absolute minimum at C. Okay, so C is the input. Okay, so C is the input, and this input, as the rule of function applies to it, it produces an output, and the output is f of C, and that is the max value. So that's the maximum. That is the maximum value, maximum output for the function. Similarly, for absolute min, okay? So this is going to be absolute minimum. And after this definition, we define local max and local minimum. Local max and local minimum, the narratives are the same, except where the changes happens at where, right? For absolute max is for all the x in the domain, but for local max is for all the near C, in the neighborhood of C. Okay, then we say f has local max at C. For local minimum, it's the same. Okay, it's similar. A local minimum is also that it's in the neighborhood of C instead of in the whole of the domain for all of x near C. Okay, so let me change the fonts to that. Okay, so f has a local minimum. There's a local minimum. You can see local max, local min, absolute max, and absolute min. Its definition is very much dependent whether the max is local, okay, or in the entire domain. So with these definitions, we have introduced Fermat theorem because we want to find maximum, minimum in many cases, absolute max, absolute min. But before we find absolute max, absolute min, we want to find local max, local min. after we found local max, local min, from among the local max, local min, we are looking for absolute max and absolute min. Okay, so the idea is first to find local max or min, and from it, from among the local max, local min, we're looking for absolute max or absolute min. Okay, so this is the general idea. So the following theorem is about local max, local min, Fermat theorem. Fermat theorem says if f has a local max or local min as C and it's differentiable as C, then the derivative of f as C is 0. Okay, we have the proof of this theorem already, so please watch the proof of the theorem either in Pronto or in Canvas. And then we're going to talk about how to find local number because of Fermat theorem. Okay, we defined critical number. Okay, a critical number is of a function is a number C in the domain, right? C has to be in the domain. So first has to be in the domain. And secondly, it's either derivative equal to 0 or not differentiable at C. Okay, so critical number. What's the relationship between local max, local min? The following statement tells us if f has a local max and or local min, okay, or local min, okay, at C, then C is a critical number. In other words, a critical number are, critical numbers are candidates for local max, local min. Okay, so let me write it down, that statement. Critical numbers of a function C, a function F, okay? We don't know how many it has, right? The critical numbers are candidates of local max or min of the function f. So, okay, from this conclusion, so in order to find local max, local min, the first thing we do, we're going to find critical number. What are critical numbers? After we found low critical numbers, we have found and these are the local max, local min. These are the candidates for local max or local min. Okay, so candidates for local max, local min. And from among these local max, local min, we will, if we require, we will find absolute max or min. Okay, so this is the general, trajectory to find local absolute max. So this is our strategy. Okay, strategy to find absolute max or min. Okay, so you can see finding critical numbers is very, very important. By the way, I emphasize in class many times, you must know how to prove, you must know what the statement of Fermat theorem and know how to prove it. Okay, now let's look at an example. The first one I take from homework. Okay, let's find critical numbers. Critical numbers. Okay, so we're gonna bring the critical number definition with us. Okay, we're gonna work on some examples of how to find critical numbers. Okay, the first example, this is a function, this is f of x equals to 4 plus a third of x minus half of x squared. Okay, we want to find critical numbers. And obviously this is a polynomial. Polynomial is continuous everywhere in its domain. It's also differentiable everywhere in its domain. So when we're looking for critical numbers, there will not be a place where, you know, function is not differentiable, or we're only going to find the the values for which the derivative is 0. So we're going to go ahead to find derivative of the function. So f prime of x, that's equals to, the derivative of 4, of course, is 0. The derivative of a third of x is 1/3. Subtracting derivative of half of x squared, and that's going to be the derivative of x squared is 2x. Okay, and in the end, we have 1/3 subtracting x. So we're going to set it equal to 0. We're going to set derivative equals to 0 because we're looking for such number that, you know, those are the critical numbers. So we set it equal to 0. As a result, and 1/3 minus x is 0. And in the end, we get x equals to 1/3. So that is the critical number. Okay, so this is the first example. So this is a general steps. And of course, sometimes the question may get a little bit more complicated, and we may have to work a bit more to find those numbers. Okay, so let's look at the next one. And this function is f of x equals to 2 times x raised to the power 3 minus 3 times x squared, subtracting 36x. And this is a polynomial again, differentiable everywhere. So we will not have critical numbers in the category where the function is not differentiable. So let's just take the derivative of this function. And that will equal to 6x squared, subtracting 6x minus 36. Okay? Because we're going to set it equal to 0, so looking ahead, it's a good idea to make it into a factored form. So we got x, we factored out the 6, x squared minus x minus 6. And factor it, so we make it easier for the next step, right? Factor x squared minus x minus 6 is x plus 2 times x minus 3. And then we're going to set the derivative of the function equals to 0. And the consequence is that x plus 3 multiply x minus 3, x plus 2 times x minus 3 must be 0. So if we can use principal number 5, right? So x plus 2 equals to 0, or x minus 3 is equals to 0. So in the end, we got 2 critical numbers. And the other one is x equals to 3. So these two are the critical numbers for the set function in example number 2. Okay, you can just you can keep it as x equals to -2, which are negative numbers, or 3, or you can use C. Really, it doesn't matter, okay? The next example, I'm going to choose one with a little bit more, actually, yeah, let's just keep going, okay? It's a function. I'm going to call it f of x. Oops, f of x equals to x minus 1 over x squared minus x plus 1. Oops. In this case, okay, it is a rational function. So the domain is a question, right? Because when we look at the critical numbers, critical number has to be in the domain, right? So we want to take a look at the domain of the function. So the domain of this function, and we're going to set the denominator equals to 0. We can set it not equal to 0. So we set equal to 0 so that any number we found will be excluded from the domain, okay? So we have this quadratic equation, but this quadratic equation, as you can see, if you graphed it, right, it's a curve that entirely above x-axis. Okay, let me show you. It's okay, it's entirely above x-axis. Okay, so then you say, what if I don't, I cannot use a calculator? Well, if you cannot use a calculator, that's not a big deal either, because we can look at, if you don't have a graphing tool with you, you can look at this quadratic formula and look at the discriminant b squared minus 4ac. Okay, b squared minus 4ac, b is -1, that's squared, minus 4 times a times c. C is 1. Okay, you can see we have 1 minus 4. This is less than 0. This tells us that this quadratic equation has two complex number solutions, meaning that there's no real number solution. Okay, so no real number solution, which also means that the quadratic curve does not touch x-axis. So in other words, x squared minus x plus 1 will never be 0. Will never be 0 for any real number. For any real number. Okay, we're not considering a complex number. So the domain of this function is from negative infinity to positive infinity. Okay, so we don't have to worry about that domain. Okay, all real numbers are in its domain. So next, let's find the derivative. Okay, so we're gonna find derivative of the function. And quotient rule, right? So we have a denominator being squared. And on the numerator, we differentiate x minus 1, that gives us 1, and multiply the denominator, subtracting x minus 1, multiply the derivative of the denominator, which is a 2x minus 1. And when we simplify this numerator, we keep the denominator, right? So we get rid of the multiplied by 1 move that, we FOIL this piece. Okay, so let's FOIL this piece. If we FOIL this piece, let me bring it down so make it easier, right? So we basically FOIL x minus 1 times 2x minus 1. So we get 2x squared, 2x squared minus x minus 2x plus 1. Okay, continue. To simplify, we're going to open up the bracket, right? When we open the bracket, everything changes sign. So this is a plus. Of course, this is 3x, right? This is plus 3x, and this is a minus 1. And then combining like terms, what do we get? Combining like terms, we got a negative 2x squared, take away 1 plus x squared, so we have negative x squared. So negative x is 3x, that makes 2x. And positive 1, negative 1, that makes 0, right? So you just combine these terms and we usually get this one. And of course, we prefer the factor form. Okay, we prefer factor form. We're going to prefer, we're going to factor the numerator. We're going to pull out the x. So that's going to be just negative x plus 2. All right. Now, it's time to determine the critical number. First of all, we look at the definition, right? Is there any number where the derivative is not defined, right? Well, the denominator is x squared minus x plus 1 squared. And we need to set this not equal to 0. But we know from previous calculation, the denominator will never be 0. The domain is all real numbers, right? So f prime is the domain of the derivative is the same as the domain of f, right? So there's no point where f is not differentiable. So we don't have this category. So we only have the derivative equal to 0 category. So we're going to set, right, the derivative equals to 0. Okay, let me write it down this way. That's the derivative, right? If the derivative is 0, denominator cannot be 0. The only chance for the derivative equal to 0 is the numerator equal to 0. So that is leading to the numerator equals to 0. So we ended up solving this equation, which will get x equals to 2 or x equals 0. So our critical numbers are x equals to 0 or 2. So we got 2 critical numbers here. Okay. Now, let's look at another example. Okay, so this is going to be example number 4. So we haven't get a chance to see where the derivative is undefined, right? So we're going to see that example. I think this one is going to be it. Okay, h of t is equal to t raised to the power of 3/4, subtracting 2 times t to the power of 1/4. Okay, domain We first determine the domain for this function. We look at this is basically, fourth root. The domain is t is going to be greater than or equal to 0. So that's the domain, right? You take fourth root of anything. The domain is t greater than or equal to 0. And next, we're going to find the derivative of this function. Okay, so power rule. So we're going to have 3/4 t raised to the power of 3/4 minus 1. Acting 2 times, right? Power rule, 1/4, and t raised to the power of 1/4 minus 1. Power rule. Oops. And now we're going to have to do some reducing. 3/4 minus 1 is negative 1/4. Okay, so that's going to be negative 1/4. So the 3/4 minus 1 is negative 1/4. Subtracting 2 times a quarter, that's going to be 2 times 1/4 is 1/2. And t raised to the power of 1/4, subtract 1, and that's going to be negative 3/4. There. And what are we going to do with it? The general rule of thumb of handling this kind of situation is to factor out the power of the lowest value. Let me say it again. The general rule of thumb is to factor out the exponent of the lowest value. So comparing to negative 1/4 and negative 3/4, the lowest value obviously is negative 3/4. But the first term, well, the second term has the lowest quarter, but the first term does not. So we're going to make it. Okay, so we're going to make it, we're going to multiply t to the power of a negative 3/4. Okay, but then the equal sign will not be balanced. So at the same time, we're going to multiply t raised to the power of positive 3/4. So what happens here is that we have t to the power 3/4 multiply t to the power negative 3/4. These two have the same base. 3/4 plus negative 3/4, that's going to be 0. So t to the power 0. T to the power 0 is equals to 1. Okay, so we basically multiply by 1. So let me write it down here. So put that, you don't have to show your reader. I just want to show you. This equals to t raised to the power of positive 3/4 subtracting 3/4. That's equal to t to the power of 0. T to the power 0 when t is not a 0, that equals 1. Where did I learn that? Well, it's the power rule. Okay, b to the power m multiply b to the power n is equal to b raised to the power of m plus n. That's where we learn it. We learn it in algebra. Okay, so by multiply by 1, anything times 1 stay the same. We generated, okay, what we did is we generated t raised to the power of negative 3/4. Okay, so t raised to the power negative 3/4. We're going to factor this out. We're going to factor this out. Boom. Okay, so we factor this piece out. And what do we have here? Right? what we have here is that we're going to add the exponent here, and that's going to be negative quarter adding 3/4. So that's going to be t raised to the power 2/4. Okay, t to the power 2/4 is 1/2, right? Simplified. So now let's look at this question, right? And of course you can say, oh, I want to factor out the 1/4. You can do that. You certainly can, right? We can do it now, right? We don't have a quarter here, so you could do that. So again, we're gonna have 2/2, right? 2/2, that makes 4, and this makes 4. So if I take out the 1/4, right? So this will be left with 3. And this is out, so this is going to be 2. If you want, okay? Anyway, so we factored out the quarter with multiply t to the power negative 3/4. And remember, we're looking for critical numbers, okay? And we just got the derivative. And we also want to write everything in positive exponents. So now let's see what we got, okay? We get 1/4, so this part we can just keep there. But we have a t raised to the power negative 3/4. So we're gonna, if we want to write a positive exponent, so we're gonna have to put it here, become positive exponents. Okay, maybe this is better. This is better looking, right? This is better looking. So far, so good. All right, so we got a denominator and we got a numerator, right? We have basically, this is a root t. Okay, this is a square root of t. Okay, that's the square root of t. Okay, t to the power half is square root of t. And this is t raised to the power 3/4. And now let's look at the domain of the derivative. Well, t is in the denominator, so this time the domain is what? T has to be larger than 0. It has to be larger than 0. So the function, the domain of the function is t greater than or equal to 0, and the derivative is greater than or equal to 0. So there is a number t equals 0, right? So t equals to 0 is a critical number. Is a critical number because it is in the domain of the function, which is h, but what? But h of t is not differentiable at 0, right? Or the derivative does not exist at 0. We found one critical number. What else critical number are we going to find, right? Well, yes, we're going to set the derivative equal to 0. So we're going to set, okay? We're going to set the derivative function equals to 0. Of course, this is going to be in the domain of the derivative. If the derivative function is 0, denominator cannot be 0, so numerator must be 0. So that's how we get this equation, okay? Parentheses can be removed, okay? And we can solve for t. Let's see if I missed anything. Oh, we didn't need this stopped, right? All right. I don't think we have any other issue. Then we're going to solve for t. And what do we get? We're going to add a 2 on both sides. So 3 times root t equals to 2. Right? We know t is positive. Okay, we're doing all of this work in the domain of h of the derivative of h of t. And root t equals to, we divide both sides by 3, and root of t equals to 2 over 3. And then to solve for t, we just have to square both sides. Okay, so let me do this. We are going to square both sides. We're going to square both sides. When we square both sides, the left-hand side is t, the right-hand side is 4 over 9. Note, okay, just to refresh our memory, we put a note here, okay. As we indicated that the derivative, well, the square root of x squared is equal to what? It's equal to the absolute value of x. However, the square root of x and that is squared, that equals to x. We talk about that. The reason is because the domain, right? This piece domain is x greater than or equal to 0. This piece domain is all real numbers. Anyway, so that was just a brief review of some basic algebra knowledge. And here we go. How many critical numbers we have? We have 2 critical numbers. They are t equals to 0, and the other one is 4 over 9. We went over a couple other questions in the class, so I'm not going to go over them again in this video as I don't want to make it too long. If necessary, I could make another one if there's questions. But anyway, thank you for watching.